Everything around you feels solid and predictable. Your phone, the floor, your own body, all of it seems real in the most obvious way. But deep inside every atom, that certainty completely disappears. Objects stop having exact positions, causes stop guaranteeing effects, and reality itself becomes uncertain. This isn't science fiction. This is how nature actually works, and Richard Feynman warned us about it. When we talk about reality in everyday life, we rely completely on intuition built from our daily experiences. Objects appear solid, they occupy clear positions in space, and they move along definite paths. If you place a book on a table, you know exactly where it is. If you throw a ball, you can trace its motion from start to finish. For centuries, scientists believed this common sense picture of reality must remain true at every scale from planets down to atoms. It seemed reasonable to assume that atoms were simply smaller versions of the objects we see around us, obeying the same logical rules, just on a tiny scale. However, once physicists began to seriously investigate the atomic world, this comforting assumption collapsed, revealing a reality that no longer aligns with human intuition. Inside an atom, the idea of objects having precise locations begins to fall apart. Electrons, for example, do not sit at specific points in space like tiny beads. They cannot be tracked along neat, predictable paths. Instead, their behavior is described using probabilities, not certainties. This means that even in principle, we cannot say exactly where an electron is at a given moment. We can only calculate the likelihood of finding it in a particular region if we choose to look. This is deeply unsettling because it contradicts the basic way our minds understand existence. In everyday reality, something either is somewhere or it is not. At the atomic level, that clear distinction simply does not exist. Time and motion also lose their familiar meaning inside an atom. In the classical world, motion is smooth and continuous. Objects move from one place to another through a series of intermediate positions. But in the quantum world, particles can appear to jump between states without passing through the space in between. These jumps are not the result of missing information or flawed measurements. They are a fundamental feature of nature. This forces us to abandon the idea that reality is always continuous and predictable. Instead, atomic reality behaves more like a set of possibilities that suddenly resolve into outcomes rather than a story that unfolds smoothly over time. What makes this breakdown of intuition even more striking is that it is not a rare or exotic phenomenon. It happens constantly everywhere. Every atom in your body, every atom in the air around you, is governed by these strange rules. The solid ground beneath your feet feels stable and reliable, yet its stability emerges from countless atomic interactions that individually make no intuitive sense. The familiar world is not evidence that reality is simple. It is evidence that complexity can hide strangeness extremely well. What feels normal to us is actually the large-scale average of deeply unintuitive behavior. Richard Feynman emphasized that the problem is not that quantum mechanics is poorly understood or incomplete, but that human intuition evolved in a world where quantum effects are hidden. Our brains are tuned to survive at human scales, not to grasp the true nature of reality at its deepest level. Inside an atom, nature does not follow the rules we expect, and it never promised to. The breakdown of intuition is not a failure of physics. It is a reminder that reality is under no obligation to make sense to us. In everyday life, observation feels passive. You look at an object, and it simply reveals what was already there. Whether you observe a parked car or ignore it, its position does not change because of your attention. This deeply ingrained assumption shapes how we think about reality itself, that the world exists in a definite state independent of whether anyone is watching. At the atomic level, however, this assumption breaks down completely. Observation is no longer a neutral act. When physicists measure a quantum system, they do not merely uncover hidden information, they actively influence the outcome. The act of measurement becomes part of the physical process, not something separate from it. Before a measurement is made, particles such as electrons do not possess definite properties in the way classical objects do. An electron does not have a single, well-defined position or momentum waiting to be discovered. Instead, it exists in a combination of possible states, each with a certain probability. These possibilities are not just a reflection of our ignorance or lack of precision. They are a real feature of nature as described by quantum mechanics. When a measurement takes place, one of these possibilities becomes actual, while all the others disappear. This sudden transition from many possible outcomes to one concrete result is known as the collapse of the wave function, and it represents one of the most profound departures from classical thinking. What makes this idea so unsettling is that the outcome of a measurement cannot be predicted with certainty, even in principle. Physics can tell us the probabilities of different results, but it cannot say which specific result will occur in any individual experiment. This means that reality at the atomic scale is not fully determined until an interaction forces it to be. The universe seems to wait until a question is asked before providing an answer. This challenges the notion of an objective reality that exists independently of observation, replacing it with a picture in which reality and measurement are deeply intertwined. Experiments have repeatedly confirmed this strange behavior. In famous double-slit experiments, particles behave like waves when not observed, creating interference patterns that suggest they pass through multiple paths at once. Yet the moment detectors are used to observe which path a particle takes, the interference pattern disappears, and the particle behaves like a localized object. Nothing about the experimental setup changes except the act of observation, yet the outcome is dramatically different. This demonstrates that observation is not just revealing reality but shaping how reality manifests. Richard Feynman emphasized that this is not a limitation of experimental technology or a temporary gap in our understanding. It is the way nature works. There is no deeper, hidden layer of classical certainty waiting to be uncovered beneath quantum mechanics. Attempts to restore a comfortable, observer-independent picture of reality have repeatedly failed or led to interpretations that are even stranger. Feynman's honesty was in accepting this discomfort rather than trying to explain it away. He understood that quantum mechanics does not tell us what reality is in a philosophical sense. It tells us what will happen when we interact with it. The unsettling conclusion is that knowledge and existence are not as separate as we once believed. At the smallest scales, asking a question of nature changes the answer you receive. Observation is an act that participates in reality rather than standing outside it. This does not mean that human consciousness magically creates the universe, but it does mean that interactions, measurements, and observations play a fundamental role in determining physical outcomes. Reality at the atomic level is not a fixed stage on which events unfold. It is a dynamic process that crystallizes into definite facts only when forced to do so. In classical thinking, it feels natural to imagine that every object is a thing with a clear shape, a definite position, and a predictable motion. When people first learned about atoms, they carried this intuition with them and pictured electrons as tiny solid particles orbiting a nucleus, much like planets circling the sun. This image is still common in textbooks and diagrams because it is simple and visually comforting. However, this picture completely fails to describe what electrons actually are. At the atomic level, electrons do not behave like miniature objects moving along fixed paths. Instead, they are best described using mathematical functions that represent probabilities, not physical trajectories. An electron in an atom is not located at one precise point in space until it is measured. Before any measurement, it exists as a spread-out probability distribution that describes where the electron could be found if an observation were made. This distribution is not a cloud of matter or a fuzzy particle drifting around. It is a mathematical description of potential outcomes. The electron does not travel through space like a tiny ball. There is no hidden path that it secretly follows. Asking where the electron really is between measurements is not a meaningful question in quantum mechanics because location itself is not a defined property until interaction occurs. This probabilistic nature is not due to experimental limitations or imperfect instruments. Even with ideal measurements and complete information, quantum mechanics does not allow exact predictions of an electron's position or motion. What it provides instead are precise probability calculations that have been tested and confirmed with extraordinary accuracy. This means that the uncertainty is not a flaw in our knowledge, but a fundamental feature of how electrons exist. Nature itself operates probabilistically at this scale, and electrons embody that principle. The wave-like description of electrons becomes especially striking in experiments where individual electrons create interference patterns. When electrons are fired one at a time through a double-slit apparatus, they gradually form a pattern on the detection screen that only waves should produce. Each electron seems to interfere with itself as if it passes through multiple paths simultaneously. Yet when detected, each electron appears as a single localized point. This behavior cannot be explained by imagining electrons as tiny particles following definite routes. It only makes sense when electrons are treated as probability waves that collapse into a specific outcome when measured. Richard Feynman often emphasized that trying to force classical images onto quantum behavior leads only to confusion. He argued that electrons are not sometimes particles and sometimes waves in the usual sense. They are something entirely different that does not fit into everyday categories. The mathematical framework of quantum mechanics describes them accurately, but the mental pictures we try to attach to those equations inevitably fail. This is why Feynman warned that no one truly understands quantum mechanics in an intuitive way. Understanding in this context means accepting the limits of intuition. The idea that electrons are probabilities rather than objects challenges deeply held assumptions about what it means for something to exist. In the macroscopic world, existence is tied to definite properties, location, motion, and shape. In the atomic world, existence is tied to potential and likelihood. An electron exists not as a thing in a place, but as a set of possible outcomes governed by precise mathematical rules. The solid, predictable matter we experience emerges from vast numbers of these probabilistic interactions averaging out. What feels concrete and stable is built on foundations that are fundamentally uncertain. This realization forces us to rethink reality itself, not as a collection of solid objects, but as a web of probabilities that only appear solid at large scales. In the everyday world, certainty feels natural. If you know the starting conditions of a system well enough, you expect to be able to predict exactly what will happen next. This idea comes from classical physics, where the future is determined by the present with perfect precision. If you know the position and speed of a ball, you can calculate where it will be at any later time. For centuries, this way of thinking shaped humanity's understanding of reality itself. The universe was imagined as a vast machine, running according to fixed laws, where uncertainty was merely a sign of incomplete knowledge. At the atomic level, however, this picture collapses, and certainty is replaced by probability in a way that cannot be avoided. In quantum physics, even with complete information about a system, exact predictions are impossible. The laws of quantum mechanics do not tell us what will definitely happen. They tell us what is likely to happen. This is not because nature is hiding information from us or because our instruments are too crude. It is because uncertainty is built into the structure of reality itself. The famous uncertainty principle shows that certain pairs of properties, such as position and momentum, cannot both be known with unlimited precision at the same time. This is not a technological limitation, but a fundamental rule that governs how the universe works at small scales. As a result, atomic events are governed by probabilities rather than certainties. When an atom emits a particle or absorbs energy, there is no exact moment that can be predicted in advance. Physics can only calculate the probability that such an event will occur within a given time. Even identical atoms prepared in identical conditions will behave differently over time, not because of hidden differences, but because randomness is an essential part of their behavior. This randomness does not mean chaos or lack of order. On the contrary, quantum mechanics provides some of the most precise predictions ever made in science, but those predictions are statistical in nature. Richard Feynman embraced this probabilistic view without trying to soften its implications. He made it clear that the universe does not operate according to human expectations of certainty. Nature, as revealed by experiments, simply does not allow complete predictability at the deepest level. Feynman emphasized that the role of physics is not to make reality feel comfortable, but to describe it accurately. Accepting probability as fundamental requires giving up the idea that every event has a clearly traceable cause that determines its outcome with certainty. What makes this shift so profound is that it forces a redefinition of what scientific explanation means. In the classical worldview, to explain something was to show exactly why it had to happen the way it did. In the quantum worldview, explanation often means showing why certain outcomes are more likely than others. The question changes from what will happen to what are the chances. This represents a radical departure from everyday reasoning, yet it is the framework that consistently matches experimental results. At larger scales, these probabilities average out, creating the illusion of certainty. When trillions of atomic events occur together, their random variations cancel out, producing stable and predictable behavior. This is why the macroscopic world feels deterministic even though its foundations are not. The certainty we experience is an emergent property, not a fundamental one. Beneath the surface of solid objects and reliable cause and effect lies a world governed by chance. The universe is not a clockwork machine at its core, but a probabilistic system whose apparent order emerges from uncertainty itself.